So the last speaker of this deep dive session will be Maxence Noble, PhD of mine, Arnaud and Valentine. We'll talk about the recent work we did on tree-based diffusion Schrödinger Bridge application to Wasserstein Barycenters.
Thank you. So just to begin with, it's not really linked to diffusion models. I don't have the introduction for diffusion models, so I hope it will be good. It's much more related to optimal transport. So I would like to begin with an introduction to optimal transport. And if you have any question during this introduction, please interrupt me and ask your question. So the idea is to extend the problem of the Schrödinger bridge to a tree-based setting. And what we observe is that with this configuration, we can solve the Wasserstein Barycenters problem. So we'll talk about this. So I will make a recap on optimal transport, how it is linked to Schrödinger bridge, and then how we can proceed in our framework. So basically, the idea is that when you consider probability distributions in machine learning, it has to do with some density. If you want to do some estimation for your Forster distribution in the Bayesian setting, if you want to do computer vision, you may want to generate some images which look like your samples, so kind of approximate a probability distribution in a really high dimensional space. But the idea is, how do you compare distributions? How do you provide intuition on how these distributions are linked to each other, how they are close? And so the idea is to use optimal transport. So optimal transport is a field which has gained recent interest, but there are techniques which date back to like the 50s, the first techniques, and it's like a very powerful tool to compute such things such as comparison between distributions. So the idea is the following. So this is a formulation from Kantorovich. You have a cost function. The idea is that you have two distributions. So I call them mu naught and mu1. And what you want to do is kind of compare these distributions. And so the idea of Kantorovich is to find a plan, basically. So it's just probability measures defined on RD times RD. And the idea is that you want to minimize the expectation of the cost between your two variables. One which has the marginal mu0 and one which has the marginal mu1. And so you optimize over all the measures defined on this set with the constraints that the marginals at some 0, at some 1 equals your marginals, right? So what's interesting with this formulation is that if you consider the classic cost, which is the quadratic cost, so quadratic cost is like the most used cost in machine learning, because it has convexity property. And so if you consider quadratic costs, you end up with the Wasserstein 2 distance. So what's interesting here is that it's actually a distance. I mean, if you want to compare your distributions, mu0 and mu1, you may want to compute this distance, which is simply the infimum of the cost function that you have defined above with the quadratic costs. And so it's really hard to compute it as long as the dimension increases, because you have to solve this kind of problem with some constraints and over a high dimensional space. So it's really, really not helpful. But I will show you some regularization of this distance, which is a little bit simpler to compute. And so the idea is that you have some targets, you have some source, so the red and the blue marginals. And what you do is that you want to find the plan which minimizes the cost defined over your set. So now we have seen how you compute optimal transport for the quadratic cost between two marginals. But the idea is, once you have more than two marginals, how do you do? It's a simple extension, actually. So you still have your cost function, but this time it's with more variables. And the idea is that you define a subset. So this is this S. You have L plus 1 marginals, and you define a subset. And what you want to say is, I have cardinal of S constraints on the marginals. So you are given this mu I. So in the previous case, we had L equals 1, and we had 2 constraints. But now we want to be more general. So you consider L plus 1 marginals, and a subset of these marginals are constrained. So these are the mu I. And then you still want to minimize the expectation over a plan, but this time with the number of variables that you're considering. And it's the same problem. So you could consider, for example, still the quadratic cost, but this time it's more interesting to, create some pairs along your variables. So if you consider this cost, which is simply a combination of a quadratic cost between one variable and the other one, so you have L variables, you end up with what we call Wasserstein Barycenter. So that's the definition. It's simply a marginal. So this is the marginal knot, which minimizes this combination of Wasserstein distance with the other marginals. So basically, you have L marginals, and you want to find the barycenter in the Wasserstein distance in the space, which minimizes the combination. And so there were lots of studies, experimental studies on this problem. So if you consider this this picture, in 3D, this set of points, and this set of points, you can compute Wasserstein barycenters. So that's linearly increasing in the coefficients between this figure and this figure. So this is a barycenter with different coefficients, and these two. So it's a problem that we can solve, actually. It becomes more painful as long as the dimension increases. We can solve it in a regularized version. So now we have multiple marginals. What I'm interested in is, okay, I'm gonna consider some organization of marginals in terms of how my marginals are linked to each other. And so I consider a tree-based setting. So basically, what you have is an undirected tree. So that's mainly a graph where you don't have any cycle, and it's one component. And so you have your set of edges, your set of weights, and your set of vertices. So this is a paper which computed Wasserstein barycenters with some link in the tree-based setting, and in their applications they considered actually the position of some parts of the body across time. And the idea is that what you will fix in your tree-based setting is the extremities of your bodies. So these are the little green dots that you see. Right? And so this is a tree. You don't have any cycle. You just have one component. Okay. Right. Now consider that every dot here is kind of a marginal. And what you want to consider is a tree-based optimal transport problem, but with this kind of organization. And so if we simply extend the quadratic costs that we saw for the Wasserstein barycenter setting, we can define this kind of cost, still quadratic, but this time we're gonna impose links between the marginals that are linked in our tree. Right? And we have these coefficients, which can be linked to some edge weights in our tree. And so if you consider this quadratic cost, which decouples actually along the edges of the tree, what you get is something which is more general than just Wasserstein barycenter. This is called Wasserstein propagation. So basically, you have some constraints. So let's say I have my constraints, which are the green leaves actually of my tree. What I want to do is to find the marginals on the central nodes that solve this optimization problem, the minimization of the Wasserstein 2 distance. So you have an optimal transport problem. You say, I'm going to use this quadratic cost. What you end up with is simply a Wasserstein propagation problem. And so if you consider a tree which is a tree which is star-shaped. So basically you have a central node with leaves that are linked to this central node. If you compute this in this case, you recover the Wasserstein barycenter. So now the question is, okay, how can I solve it? Can I solve it in unregularized manner or regularized manner? And that's what we're going to see. So entropy regularized optimal transport is really important nowadays, because when people try to compute optimal transport, they actually end up with something which was really huge in terms of computations, because if you have like in discrete setting, if you have n points in your discrete measures, for example, what you end up with is an algorithm which is in a big O of n at the power 3. So that's not good for real world setting. And so what people consider, so this has to do with the person who actually proposed some well-optimized algorithm is Couturier, so quite recently. And so what you consider is simply adding a regularization of your plan with your expectation. So how do you do? You simply have an hyperparameter, which is epsilon, and the idea is the more epsilon goes to 0, the more you recover, in theory, your optimal transport plan. So under some conditions, obviously. You could see this as simply having a constraint on the entropy of I, simply increasing the entropy such that at the end you're smoother than if you were considering the real optimal transport problem. And then you have this new, which is simply a measure that you want to constrain to. If you consider a Gaussian, you may want to have something which is smoother in a Gaussian way, right? And so if you consider this, you have in 2 dimensions. So actually these are discrete measures. This is a probability matrix, your plan. What you do is you can start with, so gamma here is epsilon. You start with a pretty high parameter. And what you do is simply you decrease your parameter. And what you hope to is recover the true optimal transport plan, which is not smooth at all, right? So you start with something smooth, and what you expect is to recover the true optimal transport plan. And so what's really important in this KL, what do you use as epsilon, what do you use as nu, because it has a huge impact on your results. And you still have your multi-marginal setting when you're considering a subset, your constraint marginals, and so simply add an entropic regularization. Is it good for optimal transport or? All right. So now I'm going to speak about Schrödinger Bridge. So first, what is Schrödinger Bridge and how it is related to optimal transport? The idea with the Schrödinger Bridge is that you have, so it's a continuous time setting. What you have is a time horizon with some reference path measures. So you can consider what we saw in the previous talks, Wasserstein process, running motion process, basically. And you have some marginals that you constrain at time 0 and time t. What you want to solve is this kind of thing. You want to minimize the quadratic divergence between some path measure, which have these constraints at time 0 and time t, along your reference path measure. Actually, if you consider something which is Markov for your Schrödinger bridge, what you end up with is this formulation, what we call the static Schrödinger bridge problem. You simply consider actually the coupling between time 0 and time t, and you're gonna solve something which is way simpler, just a measure with 2 variables, which have these constraints, nu0 and nu1, and you consider so the coupling of your reference path measure. And so how they are related. So Valentin told some words about it, but simply you can make a link between the static and dynamic formulation by seeing that your solution of the true Schrödinger bridge problem is simply your optimal coupling from this problem, the static one, with the condition path measure from Q. So if you want to solve this thing, actually you can solve the static version, which is way easier to compute, and then adding this little chunk. But now how it is related to optimal transport? Actually, if you consider something which is like a process, so you could have A equals 0 with the Brownian motion. What you have is an entropic optimal transport with quadratic cost. And the idea is that you have a relationship between your T and your epsilon. So something that, for example, if you consider the Brownian motion, the the smaller you take t, the smaller your regularization parameter will be in the optimal transport setting. So you really have to think for the following slides that t is linearly proportional to epsilon. So the idea is, okay, I may want to solve the Schrödinger bridge. Okay, I'm going to use the entropic optimal transport version. And so how do you do? So this is called in the continuous setting, the iterative proportional fitting per shader. So it's simply the continuous counterpart of the well-known Sinkhorn algorithm. And so this is an iterative procedure where you have alternate projections. So what you want to solve is a minimization problem with two constraints. So you say, okay, I'm just gonna alternate between these constraints. And so the idea is that you start from your path measure. And then what you do is simply you project with the same loss as previously, with the previous iterate, you project along the first constraint. And then at the iteration after, you project along the second constraint, right? So that's the idea. But now if you actually compute this loss and you want to find the minimizer, it's simply you simply have that this is given by the time reversal of the previous iterate. So Valentin made the computations. I could make it just after the talk. But if you really write this scale and you marginalize along this marginal, what you end up with is imposing this marginal and then having this time reversal of the reference measure. And then you alternate from one constraint to another constraint by computing the backward, the time reversal measure. So that's how you do. But in this setting, once again, you are in continuous time, so we will do some kind of time discretization. And so now this is the linked with diffusion models. So I was just saying that the R is the time reversal operator. So you compute simply the backward measure. And so if you have some SD with this kind of form, obviously, as we saw previously, if you have access to the true score of the patch measure, so the gradient of the light density with respect to the Lebesgue measure, then you can compute your time reversal. But the question is, how do you compute this? So we have plenty of machine learning tools to compute this. So actually solving the Schrödinger bridge problem is simply computing time reversal, basically. But you alternate between, I start from new 0 and then I start from new 1. And so Valentin proposed some algorithm, which he called diffusion Schrödinger bridge algorithm. And so the idea is simply you replace your continuous time setting by some discretization. So for example, the other Maruyama discretization, and you compute this discretization, for the forward and the backward SDs. And then you just have to approximate your scores. So you do it by what we saw previously, so the score matching loss. And what you end up with is something like this. So you start from your, so this is the first iteration, this is the 5th iteration of the algorithm. When I say I compute the forward, it's simply I have the constraints that at time 0, I have to be equal to my true marginal, the marginal which I want to generate from, for example. So this is this S. And at the end, what I want to be able of is simply having this Gaussian distribution as my second marginal. And so what you do is simply, okay, I project on this constraint and I compute the backward of the reference measure, which is the forward in this case. Okay, I end up with this. And now I start from the Gaussian noise and I compute the backward of the previous SD while learning the score. Okay, I end up with this. And as long as you get more iterations, what you end up with is having the good marginals at time 0 and at time t. And the idea is how does it converge? So it's not the subject of this work, but you may have some results under mild assumptions, I would say. And what's interesting in this algorithm is that this thing. So remember what I said earlier is that your regularization parameter in the optimal transport setting is linearly linked with t. So the smaller you take t, the smaller your regularization is. So your idea in a optimal transport setting is to take t really low. And what we have in this algorithm is that, so this is, while in the score-based diffusion setting, you take T pretty high to get to the Gaussian noise because you have Wasserstein limit process, and you have to have some convergence at the end. Here you have constraint on the marginals, so actually you don't have to weight convergence in your SDE. So basically you can take T, which is small, not too small, obviously, otherwise you will have a problem. I had problem in these conditions, but you can take T pretty low. So this is a good good sign for solving optimum transport problem. So now I just recall the setting. So we have this regularization. So in the multi-marginal setting, I have my constraints over my subsets of the nodes. This is given by the parameter epsilon and the distribution nu, and I have my cost. Okay. So now I'm just gonna. So previously I was saying, okay, in the bimarginal setting, I have optimum transport problem, which is really equivalent to Schrödinger bridge. Okay, now if I assume that my measure nu is absolutely continuous with respect to the Lebesgue measure, then I can write this multi-marginal entropy regularized, etc. Problem as a Schrödinger bridge problem. So I mean, I'm not in a continuous time setting. You see, I don't have path measure. I'm just considering the marginals where I have constraints, or I may have not any constraint on these marginals. Okay, so how does it come? Simply, you consider this cost, which appears here in your reference measure. But the problem is that you may have trouble to see if it's really a probability measure if you don't take nu, which is well linked to C. So at this stage, we consider that this is a probability distribution, but it may not be, depending on the choice of nu with respect to C. But actually, simply if you can write it, developing the log, the exponential, you end up with this formulation, really easy. So now what we have is simply this formulation, a multi-marginal Schrödinger bridge problem, because you have several constraints, can be linked in equivalence actually to an entropic multi-marginal optimal transport problem. So the idea is, okay, maybe I want to solve this, or I want to solve this to solve this. But have in mind that what we have in the non-regularized bimarginal setting, you have this in the regularized and multi-marginal setting. Right? And so the idea is all your parameters, C, epsilon, and nu, get into pi naught. Okay, so now if I go back to my setting is I don't consider any subset of probability distributions. I'm gonna consider distribution which factorize along the tree. Okay, so I have my tree. I have a subset of my tree, and in this setting, we're gonna consider S as the set of leaves. So remember, these were the red dots along my human body. As I told you, the most common cost to consider in this tree-based setting is the quadratic cost, which decouples along the edges of the tree with the weights that are associated to the weights of the tree. And as I told you, if I don't have a proper choice of the new measure, I may not have a probability distribution for pi naught. So this, once again, this may not be a probability distribution. So what I consider in my setting is simply a potential against the Lebesgue measure, a potential in some vertex of my tree. So 3 ingredients, and what you have in the end is that if you compute this thing, so you have a quadratic cost which decouples, you have your potential. What you have is simply something which is probability distribution in the setting, and more interesting is something that has Markovian factorization. And we want to have something Markovian because in the Schrödinger bridge problem, the reference path measure is always chosen as a Markovian with Markovian nature. So in the end, you recover something which is not continuous, but with still this Markovian factorization. You mean which one? This? We're gonna see in the computations. So now just think that R could be chosen as anyone. single vertex, right? Because if you want to compute the exponential of this, you have some Gaussian distribution. So this could be at the if you condition on the previous, if you do some ancestral factorization, you see that you don't have much choice on the for the new. You have to impose something on the node, and then you follow your quadratic cost, which is Gaussian, 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 and then you end up with something which is a probability distribution. No, you don't have a proper distribution, because this is like if you see this, if you write this and you decouple along your edges, what you have is conditional Gaussian distribution following the edges of the tree. And so the only choice that you have is the choice of the first node. Otherwise, you don't have a probability distribution, and we want to have to be in the case of the Schrödinger Bridge setting. But you may consider other setting for new, but you don't have a probability measure. So it's really important to have in mind that we don't have so much choice. Given the cost, the quadratic cost, we don't have so much choice on the new. You just choose one potential on the node, and then you follow your Gaussian conditional distribution. In theory, you could choose something else, but you may not have a probability distribution. Right. So, and if you see, what you have here is your quadratic cost, and you see that actually you have conditional distribution given by the edges of the tree, which start at the node R, and these are really the variance of the given by the coefficient, and you have your quadratic cost, which gives you the Gaussian distribution. So this is conditional, following actually the edges of the tree. And what you have is only this choice of the potential on the node. So you may choose any node in your tree, and you follow with the quadratic cost the Gaussian distribution to every node of the tree, and you just have one choice of how can I choose phi r in this setting. Okay, and so now if I have something which is Markovian, I recover some kind of Schrödinger Bridge idea. If I have something which is probability distribution, this is great. So now what I end up with is a tree-based formulation of the static Schrödinger Bridge problem. I recall that I have this constraint, so the subset of the vertices where I have constraint is the leaves. So I impose marginals on the leaves of my tree. I have this mu I, and what I have is simply this pi naught, which is my reference measure. And you have two parameters, the choice of the node and the choice of the potential on the node, and you simply have this factorization. So you have something which is quite of a discretization of Brownian motion, because you have this this thing with different time, different variance. So you have like a discrete version of a Brownian motion, and the idea is what distribution do you choose on the first node before propagating the Brownian motion? Is it clear for everyone? Just the choice on the node, and then you're following your Gaussian distribution. So now I'm going to speak about a way to solve this problem. So this formulation with constraints with a pi naught given by this. And this is called TreeDSB. So just notation. So I denote K as the cardinal of S. We will see that this is kind of important. So if you want to, okay, I will explain later. But this idea is to have in mind this. So I told you that in the B-marginal setting, the epsilon coming from optimal transport problem is proportional to T. In this time, we have multiple couples, right? We have trees, so we have relations between two distributions, but on multiple locations. And so now this is depending on the weights between the node B and V prime. And you still have this this T, so what I call T, and we will see when you have to compute this thing. So I have a continuous time formulation. So to simplify between the continuous time and the discrete setting, I mean just the static version and the dynamic version of the Schrödinger Bridge. What I call the X, the operator X, is simply taking the coupling at initial time and final time on any time interval 0 t. And so what are the assumptions in this framework? So I assume that I have my mu I, which are absolutely continuous with respect to Lebesgue measure. So to answer your question, in this setting, I'm gonna choose R in the set of the ellipse, right? And then we will see, okay, if I choose something which is not in the ellipse, what happens? But now I'm just gonna choose something in the ellipse. So once again, the green nodes in the tree-based setting, and I'm gonna use as a phi something which is actually the potential given by some marginal, the marginal on the node actually. So we will see later that you can choose something else as long as the KL with this measure is finite. Have in mind that choosing this does not change the nature of the problem. Once you have your roots, which is given in one of the leaves of the tree, choosing phi r, which has some relation with the mu I corresponding to this, is not so does not create any damage. Okay, right. And so, as I told you, the idea of Sinkhorn or IPF in the B-marginal setting is I alternate between projections on the first marginal and the second marginal while solving this KL problem with the previous iterate. Okay, now I'll just extend this. So this was made by Benamou in 2015. I extend this by just computing the projections along all the constraints. And so I just follow a cycle, some cycle. I project on the first, on the second, on the third. Then I projected along everybody, and I start again. First, second, third, first, second, third. And so I compute the simple extension of the IPF with multiple marginal constraints. Yeah, sorry. So just to be clear, so if you have in this, so this where you have your marginal constraints. Let's say mu1, mu2, mu3, mu4. Okay, right. And then the gain is simply the iterations. So if I take, and this is constraint. The first iteration, you project along this, mu1, the second, mu2, right? No. And then you have the fourth, which is mu4, and then you get back. So, okay, mu1, 6, mu2. So K is simply the modulus of the iteration along the number of marginals, so that you have a cycle. Is it clear for everyone? Simply a cycle over the constraints. Just a notation for the. Yeah, a tree, not a graph. Yeah, so yeah, you can consider this, 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 and so here are your constraints. And so you project this, and you cycle. But you can consider any cycle basically, as long as everyone is concerned.
Which again, why you have to constrain multiple times doing multiple cycles?
Yeah, it's an iterative algorithm. So if I get back to the B-marginal setting, yeah, this. So simply, what you consider in this B-marginal setting, this is a great drawing. So you have your patch measure, and what you want to do is, okay, I have my patch measure. I want to project along this constraint. So at time t, I'm equal to my marginal mu1. So I project, okay, but now, if I want to solve the double constraint problem, I'm going to alternate, right? So what you have previously, you project it along the other constraint, and then you do it several times, and you hope that in the end, you converge. But now consider that I don't have two lines, but I have like big K lines. And so you alternate between these big K lines, basically. Yeah, cool. So somebody gave up. Okay, right. So now I have this this static formulation of the IPF, simply the extension from the B-marginal to the multiple marginal setting. So how can I solve this while still having in mind the dynamic version, since what we saw with the DSB, the algorithm from Valentin, is that you compute time reversal. So you have to consider in some extent some continuous time, or at least continuous time discretized version of something which is static. Because I repeat myself, but this thing is just a probability measure, which is with five states. And what you want to have is path measure along this this marginal. So what I consider, so this is a result. It's simply the extension of this static setting to the dynamic setting. Since I consider the since I have my Markovian factorization, which is given by Gaussian conditional distribution, I have actually a Brownian motion. I start from this root R, and then I propagate my Brownian motion along all the edges. So I think I have some drawing. Yeah, but this is not good. So yeah, this. So this is where you have your constraints. Let's say I choose this as R. So this is my root. What I say in the first iteration, in the zeroth iteration, is I just propagate some Brownian motion over all my tree, which is given by the the directed tree, which is given by the R. You just have one direction. Once you have one root, you just have one direction. So this is the first iteration. Simply recover the dynamic setting from the starting setting. Okay. Now, if I consider what happens there, yeah, I'm gonna display it. At time n, what you have is this constraint. So let's say that this is the constraint at time n, and this is the constraint at time n+1. And what you say is simply that if you want to compute all the path measure at times n+1, you can simply recover them as either the path measure from the direct path measures from the previous iteration, or the time reversal of the previous iterations. And so this is really important to understand. Once you have all your path measures at time n, you simply have to consider the path between your new constraints, this is in yellow, with the previous constraint. So this was the constraint at time n, this is the constraint at time n+1. And what our theorem says is that you can derive all the path measures at time n+1. So these are the green arrows, by either reversing the red arrows, because these are on the path between the previous and the new constraint, or simply having the path measures from the previous iteration. So you have two cases. Either you are in the path with you consider one node, either you are in the path with the previous constraint, then you have to compute the time reversal, or actually not in the path, like this node, it's not in the path, then you simply have the path measure. And so the extension of the Schrödinger bridge problem with two marginal constraints is simply you consider your path between the previous and the new constraints, and you operate the time reversal of these path measures. And that's it. You just have to understand it. I compute the path between my previous and the new constraint, and I reverse the path measures. So if I consider another drawing, so this thing, for example, so I propagate my Brownian motion for the really first iteration. And when I do afterwards is, okay, this is at time 1. How can I compute the path measures from this iteration? Okay, I'm simply gonna operate the time reversal of this thing. And this is the path measures from the previous iterations. So you just do the time reversal on the path with the previous constraint. And then if I consider this, I may have to reverse the time for this path measure, and this path measure, and this is already computed. as this is actually the dynamic formulation for the multi-marginal setting. Just compute the time reversal on the path with the previous constraint. And so how do we do? So as I said, in the B-marginal setting, you have two neural networks to approximate the forward drift and the backward drift. So now this is bad for me, but I have to consider 2 times the number of edges of neural networks, because I have to get one neural network to approximate this direction of the drift and this direction for the drift. So this is really huge in terms of computation. So 2 times the number of edges neural networks. And how do you compute TreeDSB? You simply consider the path between the previous and the next constraint. And what you do is you sample from this path, and then you compute the time reversal with some machine learning tools. So for example, if I consider a really simple setting, so a star-shaped setting, what I have is this marginal that I don't know. I don't have any constraint, but I have constraints on this, this, and this. Okay, so I start with pi 3. Let's say I start with pi 3. This is my first constraint. And I have my second constraint, which is pi 1. Okay, right. Assume that I have propagated some Brownian motion starting from this, right here, here. Then what I do is this dotted line, I'll simply compute the time reversal of this measure and this measure to get back to pi 3. Now I consider this constraint, and I have a new path, which is with the next constraint. Okay, so I propagate my path measure, and then I compute the time reversal. And then you do it. And you see that every edge is visited 2 times, one in the forward direction, one in the backward direction. And so you have your constraint, you compute your constraint several times, and you do it iteratively. And yeah, the cost that you have to pay is this number of networks that you train successively, because you have to have access to the previous path measures to compute the new time reversal. So you cannot make it in parallel way. You have to make it successively. So this is no good, but I don't have any choice on this. Okay, so this is the part where you could say, okay, I don't want to sell theory, but this is really just to see if things kind of work in theory, and it's not really huge. So don't be afraid. Okay, so I recall my multi-marginal setting. So now I'm going to consider a pi naught, which is a path measure. I have my constraints over the subset, not necessarily a tree, not necessarily the leaves of a tree, just a subset. I have constraints, and I have my pi naught. What can I say about the minimizer of this Schrödinger bridge problem? So the results in the B-marginal starting Schrödinger bridge problem are really well known, but it's not always obvious if you take a subset of the nodes with some assumptions on the mu. What do you consider? What is the link between the pi 0 and the mu? There was no clear results on this kind of setting. So we simply adapted the results of this work to the multi-marginal setting, and this is really natural extension of the results. So you have under condition on your mu I and a condition on the pi naught, which is not so which are quite good conditions. Actually, you can have a unique solution to this multi-marginal Schrödinger bridge problem. But what's more important is this thing. So this is really important in optimal transport theory when you want to solve a Schrödinger bridge problem, is that you can express your solution as something which is absolutely continuous with respect to the reference measure, but with some potentials. And these potentials are actually defined on the constraints. So that's really important to consider. This expression gives you actually the whole theory to state the convergence of the IPF in the B-marginal or the multi-marginal setting. So the idea that you can express with some potentials on your constraints, your solution with respect to the reference measure. These are called the Schrödinger potentials. Right, and so the idea is simply, once you have your full Schrödinger bridge problem, you consider a successively different Schrödinger bridge problem, but with one constraint, and you iterate over your algorithm, then you can prove that once you have your results for the whole set of constraints, you also have it for one constraint, but iteratively. And the idea is the following. You have actually a family of potentials for every iterates of your algorithm with respect to the reference measure. And what you actually solve in the static setting, so the IPF but not the dynamic version, it simply iterates over the potentials. You want to respect some constraint, which is at time t, I have to be equal to this marginal in this node. Okay, this has a constraint on some potential, and then you compute your iterations with these potentials. And so, based on this formulation, there were plenty of results, some quantitative, some non-quantitative, on the convergence. For now, because we have Alain in this room who's going to provide really successful things. For now, we have quantitative results, but only for bounded setting in this bounded setting for the cost. I mean, so people like Carly, people have geometric convergence of the IPF, but when they consider bounded cost. So this is not good because we have a quadratic cost, so it's not really good. But other results like Rüschendorf didn't have any quantitative results, but at least they had convergence. So we inspired ourselves from this results with two marginals to state some results on the multi-marginal setting without any quantitative results because it's really hard to get. But at least we have some convergence in total variation distance between our iterates and the true Schrödinger bridge under some assumptions on the potentials, like they are bounded in a certain way and the marginals have some properties. So this assumption is not, you cannot expect it to be true in the real world setting, but at least we have some convergence results. And so, yeah, the idea would be to, so this is not trivial at all, to extend some results. So a paper that Alain did with Giovanni Conforti, who actually, they have some quantitative results for quadratic costs. So this is really cool. But for now in the B marginal setting, and you could maybe extend it to the multi-marginal setting. Once again, it's not trivial. And the problem is that with this thing, it's only theoretical. I do not include any time discretization error from my SD discretization. I do not include any approximation error from my neural network. So for now, it's only theoretical without any practical assumption. Okay, so now I'm just gonna shed light on an application, which is the Wasserstein Barycenter. My title is Application to Wasserstein Barycenters. So I recall that Wasserstein Barycenter is simply minimizing the expectation for the quadratic costs along the plan. And now you consider some regularization of this thing with the entropy regularization. So what you say is you impose, as I said earlier with the regularized optimal transport problem, you impose that your entropy has to be higher so that you are smoother with your optimal plan. Okay, so what I do is I now consider something which is star-shaped. So this is star-shaped. You just have one central node and everybody is linked to this central node and you have all your constraints on the ellipse. So I consider this kind of star-shaped tree. I consider this regularized version of the Wasserstein distance. And so now if I consider this problem, I can actually show that this problem is equivalent to solving a Schrödinger bridge problem. And so I'm just going to spend some time on what it is exactly. So this is actually a regularized version of the Wasserstein 2 Barycenter problem. So you see, I have my combination of my Wasserstein 2 distances between my central node, which I don't know, and my constraints, the mu. But now I have some regularization. And this regularization is not trivial. You have there, there, and there. So 3 times. The first type is, okay, I have a ponderation with the weights of the edges. And you have this parameter epsilon, which comes from here. Okay, it's all right. It's not that bad. But now I have this thing, and what you observe is that you don't have a minus, you have a plus. So actually, you like removing some smoothness of your central node. So this is really cool, actually, this thing compared to this thing, because you're adding smoothness of your plan between two nodes. So think of the edges. This is like a couple distribution. But now you're removing on the central node, which we want to compute, you're removing some smoothness and you're removing L times, L being the number of limbs. So this is cool. But now there is something less cool, which is you still have some regularization on your central node, which is given by a mu naught. And so if you consider, so this is where it gets interesting. If you consider you R equals 0, so actually you take the central node for the beginning of your Brillouin motion as the node where you want to compute the Wasserstein barycenter. So you choose R equals 0, and you choose the potential as some potential of a distribution mu naught. So you may think as a Gaussian distribution, for example. So if you have this choice with this choice, then you end up with this a regularized version of the Wasserstein barycenter problem starting from the TreeDSB version. So if you solve a tree Schrödinger Bridge problem with this choice and this choice for your reference path measure, because these are the only parameters that you have to choose, then you solve actually the Wasserstein barycenter problem. So you have some trade-off to do, because this epsilon is not, you will not get the true Wasserstein problem. You will get some approximation, and it's really hard to compare this regularization with standards regularization. I mean, just imposing some regularization in the Wasserstein to distance, or only here. It's like a doubly regularization, but it's still cool to see that with some abstract formulation, the Schrödinger Bridge problem, I finally end up with Wasserstein barycenter problem. Yeah, it's depending on epsilon. Yeah, of course, yeah.
So what is the relation where we start? So 5 star is 3. So what is the rule okay, so now we have a solution for the epsilon.
Yeah, the epsilon is actually in the pi naught. If I yeah, because you can express pi star with the Schrödinger potentials as pi naughts are up this thing. You have the epsilon in the pi naughts. So actually, if you solve this Schrödinger bridge with R equals 0 and phi r, which is a potential, you end up with the Wasserstein barycenter problem, and the epsilon is hidden in this pi naught. Right. So it's for any epsilon, of course. So this is in theory, but in practice, you don't choose epsilon too small. Okay, so now my goal is to say, I have my Schrödinger bridge formulation. I may solve Wasserstein barycenter problem. And so, as I said, I have a computational limit, which is I have 2 neural networks per edge. So I just consider in this setting 3 lifts. So I have 3 edges. So I have 6 neural networks to train, which is quite hard to do. And so I just compared, so I'm not going to spend time on this, but I compared my methodology with previous regularized version for optimal transport to compute Wasserstein barycenter problem. So you could have actually the choice of the weights. I recall that the weights on the edges gives you the regularization for the time horizon on each edge. But to be simple, I just suppose that for everybody, I have the same edge. So I have like equal Wasserstein barycenter problem. I don't have any more importance on some terms. So this TVB prime is the time horizon for the path measures on each edge. Sorry. So this is once again proportional to epsilon. So I choose epsilon, and then I have my t, which is given by epsilon in the number of nodes. So as I said, the only choice that you have now to compute your Wasserstein barycenter problem is the choice of mu naught. what do you want to choose? You may want to choose something which is smooth. So in our choice, we choose something which is Gaussian, with some prior coming from the leaves. But you could basically choose anything. Just Gaussian is easy to compute. And then I have my computation trick that instead of cycling over all the leaves in a certain cycle, I do it randomly. So at the beginning of each cycle, I have a random order of the leaves that I visit, and then I reorder this order every cycle. And these are the results. So what I want to do is compute the Wasserstein Barycenter, Wasserstein 2 Barycenter between these three distributions. These are not the true distributions. These are actually the distributions that are recovered with the Schrödinger Bridge problem, because I read it myself. But what you want to do in the end is compute the Schrödinger Bridge problem. And so at the end of the convergence, you're supposed to get the right marginals at the end. So these are the marginals that we obtain after 20 iterations for the Schrödinger Bridge problem, starting from this data sets. So I choose epsilon is equal to 0.2, because if you choose something which is smaller, then your t, as I said, diffusion Schrödinger Bridge works well with small t, but if you choose something which is smaller, then it doesn't work at all. So you cannot choose something which is really smaller than this. And then I have my barycenter. So this is my barycenter where I diffuse from this node, this from this node, and this from this node. Obviously. At the end, you have your path measures that go this way, go this way, go this way. So what you expect is that with your neural network, you learn some score, and at the end, you hope that in the central node, everybody is close to each other. And so after 20 iterations, we have some sort of convergence. This is just an illustration. There is no figures here of the Ecole or anything. But you see that it's not completely fulfilling. I mean, you still have some bias coming from the data sets, like this area is kind of filled here, it's not filled here. So what we guessed is that with some marginals that are not smooth at all, we have some distortion. It's really hard to get the true Wasserstein barycenter. But if I consider Gaussian distribution, this is really great. And it does not depend on the dimension. So I run experiments for dimension 2 to dimension 256 with a small regularization parameter. And why I display as a comparison for other methods is simply the Wasserstein 2 distance between the Gaussian estimation from the barycenter that I get. So imagine that I get a barycenter, then I simply compute the mean, I compute the covariance, and I say, okay, I have a Gaussian estimation by taking the mean and the covariance. And then I say, yeah, but actually I have Gaussian distributions. So with Gaussian distributions, we know that the non-regularized Wasserstein barycenter is also a Gaussian with explicit mean and explicit covariance. And so what I say is simply, I compute the Wasserstein 2 distance between these two Gaussian distributions, the one which is estimated from the barycenter that I get at the end, and the true one. And what I say is that it's not so bad for our method. Like we're really close to the true Wasserstein barycenter of the distributions, while the other method do not really scale with the dimension. So have in mind that this is really great, our method with smooth distributions, but as I said, it's not so well good with kind of non-smooth distributions, but still. So we try to do it.
Can you comment why dimension choose worse than the
other? There is some overfitting, I think. Yeah.
For the other, no.
We do not for this one. For this one, it was really a nightmare to make it converge. Actually, what we took is that as the dimension increases, I have more neurons in my neural network. But if you choose, like for example, in this setting, at the beginning I was like, okay, I'm gonna choose a network which is like the one that Valentin used to generate things in a 2-dimension. And actually, what I end up with is something which has not converged at all. So I say, okay, I'm going to increase the depth, I'm going to increase the number of neurons, but then I have something which does not converge too. So this is like a trade-off between something which overfits, something which underfits. And so what we have is that in 2D, it's too overfitting. Yeah, it's if you want to compute the Wasserstein problem with a 2-dimension, I recommend you to use this thing, which is way. So this is a method by Arnaud in Q3.
It does not explore.
No, it's not. There is no machine learning. It's just a gradient descent of. Right. So yeah, we do not have good performance in low dimension, but in high dimension, since we have like more, we're more scalable because this is just a guess, but like the neural network can really learn something in high dimension and overfits in low dimension. And we try to do it with high dimensional objects. So now just take a look at this. I increased the regularization parameters since I increased the dimension to have something which actually works. So this is still pretty low for a setting of T. Like Valentin in his experiments chose T as 1 or 1.5. So this is the list that you can get with a NIST problem. And so what you see is these two pictures are taken from so this is a Wasserstein barycenter between 0 and 1 on the first row. And these two things are taken from non-regularized method. So actually people try to compute the true optimal plan non-regularized. And they end up with these things. So this has to do with neural network things. I'm not going to explain. And this is the method, the regularized method. So the one that we are comparing to. This thing is also using neural nets. This not, but this, yeah. So you cannot compute a barycenter between 0 and 1 with the first method, only in low dimension. But this thing, you can. And you have something which is degenerated. But here in our setting, we have something which is regularized. So you don't have something which is so clean as this, but we have still something which is quite good, I mean, compared to this. So this is really, really, really exciting. And we tried to do it with 6 neural networks. So computing the barycenter between the 4, the 6, and the 2. And there was no literature previously on the barycenter for NIST for these things. So we end up with this. You have something which looks like a 6, but you have some 2, you have some 6. So
just to be sure,
yeah,
different images are different iterations.
No, sorry. So this is at the end of convergence, the reconstruction of the data sets.
Yeah, but like your nodes have like 4 distribution of 4s, one node is distribution of 4s, the other is distribution of 6.
Yeah, exactly. You have a three. You have 3 barycenters. You may have like three samples. Yeah, but what we observed, I didn't put the picture, but they are the same actually. It's really cool. Like we have this in the paper, but the barycenter that you get, as I said, you have as many samples as edges, because what you do is you diffuse to get the barycenter. You choose one node and you diffuse to the center, right? So you have in this setting we would have 3 types of samples, but what we observe is that these samples are current between the 3 loops. I didn't put it close. But yeah, it's a good question. Like, do we have actual convergence? Because what we have at first stage is we had convergence on the marginals, but we didn't have any convergence on the central node. So you do not compute any barycenter. So this is the first time that you have something which is like kind of generative modeling with 3 data sets in the Schrödinger Bridge setting. So this is really cool, actually, to get the 2, the 6, and the 4. And something which may be interesting for some of you, which is a task which we call subset posterior aggregation. So the idea is, if you have multiple data sets, and you want to compute some poster distributions based on these data sets. You may want to compute while gathering all the data sets or while splitting the data sets. And what you have is that if you compute each poster for each data set, there is a theorem, also in this paper, which tells you that if you compute the Wasserstein barycenter between each poster distributions, you end up with a true poster distribution. So the distribution where you gather all your data in one set. And so the idea is, okay, so maybe instead of computing the poster for the whole distribution, because I don't have access to the data sets gathered, I'm gonna compute the poster distribution for each sub-data set, and then compute the Wasserstein barycenter of these posters and say, okay, this is far from the true poster. And so this is what we do with the methodology of the previous methodologies. And this is once again the Gaussian approximation thing. So this is the same distance as previously. And what we have is that in this task, so we are in dimension 42. So this is a little bit too high for the previous methods, but we are still good compared to the other methods. So this could be used. For example, Alain had the idea. If you want to have a proper prior for your Bayesian setting, you could use, as Marcelo presented, generative models. But imagine that you have several data sets. You may want to use the Wasserstein barycenters of your priors on each data sets. And then, yeah, you can do whatever you want with your Wasserstein barycenter. So at the end, what we have is something which solves Schrödinger Bridge in a tree-based setting. We state some conventions, not quantitative, and it's not so much fulfilling because we do not have a proper theorem with the approximation and discretization errors, but still it's a first step. The problem with Schrödinger Bridge are the following. When you choose epsilon, which is really too low, it doesn't work, like really not. So you have like a limit for your you cannot do annealing. I mean evolving with a low epsilon, you cannot do this. You have the bias, and the bias is really increasing. Since you have 6 neural networks, you're like accumulating errors from each networks. And so at the end, you have too much errors, and so this does not propagate well along the iterations. Because in diffusion Schrödinger Bridge problem, what you have is only 2 marginals, so 2 neural networks, and there is bias, but not as much as 6 neural networks. So if you want to have something which is really clean, it not may be adapted. And so, of course, still this we cannot do something else, but you have too much neural networks if you want to compute like a Barycenter for, let's say, 5 data sets. So it's good if you have large data sets with plenty of information, so that neural networks will be useful, but not so much. Like 3 is good. And so the idea in the future would be to provide quantitative convergence. Once again, this is hard to get, and maybe to avoid this bias, relying on some flow matching community things. So instead of having access to the whole trajectories to compute the time reversal, maybe having access to a bridge, which can spare you some bias when you compute the training of your neural net. And that's it. Thank you.
Can we imagine that basically in such optimization problem we define and first solve the sub-problem on the 2 sub-problems, the optimization problem on the 2 sub-number of the marginals, and then find a way to actually merge, basically doing some kind of, which could be called dynamic programming approach of such multi-marginal problem, because the dividing the sub-optimization,
yeah,
you solve it. And then you just have to solve the problem of the resulting 2 Barycenter again. Something that we could do also for the Barycenter.
It's a question, right? Yeah, because it does not work. Like actually, yeah, people try to compare this kind of things. Like if I only consider the couples, and I do Schrödinger Bridge between these couples, and is it far from the true Schrödinger bridge problem? And actually you can state this theoretically. Like you cannot avoid these iterations from one leaf to the other leaves and cycling it. You have to take all the marginals together, otherwise you have something which is biased, too much biased. Like it's not your true solution. And that's really annoying, but yeah, that's it. So of course, if you want to, it's a really good setting, a starship tree. But if you think of a real tree, like the one that we saw in the human body, you may have access to like plenty of neural networks, so it's not good. So it's good for Wasserstein Barycenter, but there may be another solution for this kind of tree in practice. Yeah.
You give some ideas to why you have the tree Schrödinger bridge, which only involves the chaos derivatives, is equivalent to the Wasserstein Barycenter.
Oh yeah.
As a question is the quote.
Yeah. Oh, maybe it's better to see on the paper, so that I don't make any mistakes on. It's just a way to decompose your Ecole divergence by conditioning on the previous. Yeah, that's it. You okay, right. That's it. So basically, what your assumption are is that you have something which is Markovian for pi and Markovian for pi 0. We all already know that pi naught is Markovian because we choose like the conditional Gaussian distributions, etc. But when you solve the Schrödinger bridge, you don't know at first that pi, you optimize along all the distributions that are like in your, you don't know that they are Markovian, right? So what you say is actually when you compute the true solution, when you say there exists a unique solution, this solution is Markovian, so I'm going to restrict the solutions to the Markovian ones. And so now I just make the computation for a Markovian distribution, and then you see you just decompose with your Markovian style starting from the roots. So you have the same expression on the left and on the right. Then I decompose my KL. And I condition on the previous, I do like kind of recursion. I condition on the previous, on the parent node with the conditional distribution of the child given the parents. So this is the thing. So Valentin made the calculus just for two nodes because it's really easy to see. It's like when you want to say that. So when you have this thing, it's always this. You said that this is so this is the trick that you always use in a Schrödinger bridge problem. When you have a constraint on this thing, you condition by this marginal, and then you have the KL of the conditional distribution. So this is what we do, but we do it like recursively by conditioning on the parents. Then we have the children. So only one children, because we're in several children. Sorry, one parent but several children. So you have this sum on the edges. And now what you do is simply that you know that actually this thing is a Gaussian distribution. So this pops out with the coupling, and then it remains the entropic term. And so this is the entropic term, and you rewrite the entropic term of the conditional distribution with the entropic of the joints minus the entropic of the margin. And then you end up with this thing. So you recover the Wasserstein propagation problem. This comes from the pi naught because you have something which is Gaussian, and this terms the entropic and entropic of the joint and entropic of the marginal come from the decomposition of the conditional. And since you have several in this setting, for example, since you have several children, you have this cardinal of CV being the number of children. Because what I say is I start from this node, for example. So I go here, 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 and here. And for example, yeah, here, I have several children. And so if I consider a pi, which is decomposed with this Markovian factorization, actually I recover 2 times the entropy of these nodes, since I have 2 children. But I have only once for the coupling, this coupling and this coupling. And so this is just the Wasserstein 2 regularization. And once you have your star-shaped tree, you take the central node, and the central node has 1, 2, 3, 4. So for entropy of the central node, and there is still this regularization term, which has to do with the what do you choose as pi 0 r. What is this is really the question. We choose Gaussian distribution, but what do you choose as the regularization for your central node? Like, is there and this is an interesting question. Like, is there a choice that does not incur a further regularization? Because choosing something Gaussian, you may have, if you consider, if you consider images, this not maybe adapted. Like, you don't want to have Gaussian noise into your images. So this was like a simple choice, but maybe not the best one.
Okay.
So is it clear for you, the computations?
No, the details, but yeah, let's keep it.
Yeah. But the key is you cannot do this decomposition if you don't know that pi is Markovian. And since we optimize along all the distributions, we first have to say, okay, we restrict to Markovian distributions since the solution is Markovian, and then we can say something.